Hello and welcome back to the Texas Financial Derivatives YouTube channel. In this video, I'm going to walk through kind of a really short simulation or a short implementation in Python of the Monte Carlo simulation algorithm as covered in the last video. So in the last video, you saw that I was pulling kind of just three observations to use as our approximate distribution for the present value random variable of an annuity. That's the annuity being determined by random factors itself. So it was an appropriate usage of Monte Carlo, but to compute those samples by hand was really tedious. And I think I even made an error on one of the z-scores while I was doing my computations. So as you can see, computing these things by hand is very error prone, very tedious, takes a long time. And so we're going to show an implementation of just one way that you could do these things in Python in order to help improve efficiency, improve accuracy, and improve your results when using the Monte Carlo method. So in this first cell, I'm going to kind of just talk through all these 5 cells here. In this first cell, we're going to import the required packages that we're going to be using. So we're going to use NumPy in order to set the seed for y'all to be able to replicate the results that we're going to have here in this video. That's all we're really going to use it for. And then we're going to import matplotlib in order to plot up a histogram that's going to show our approximate present value random variable distribution. Then we're going to use SciPy in order to do a little bit of random sampling. That's going to kind of take the place of that kind of intermediary method that we used in the last video where we went through the standard uniform random variable. That's going to kind of take care of all that for us, that packages. And then we're going to import pandas just to grab some summary statistics at the end and show the numerical results of our Monte Carlo simulation. So we set the seed at 42, and then we're going to define a function called trial that takes no inputs. All this really does is throws together kind of our samples for us. So it's going to take the variables that are this I, N, and K are going to be the same variables that were in the last video, the interest rate, the term, and the fixed payment for the annuity. And those, like we defined them, are going to come from these random variates of the normal distribution with mean 10% and standard deviation 1%. So that's for the interest rate. The term is going to come from random variates of a binomial distribution with number of trials equal to 5, probability of success equal to 3/4. And then finally, the payment for the annuity is going to come from random variates of an exponential distribution with average equal to 100. So then this next line here is just going to kind of throw all of those 3 variables together and output our present value observation or present value random variate to be used in our simulation. So each time this function is run, it's going to assign a new value for the interest rate, the term, and the payment, and then it's going to compute a present value, and it's going to return to us that present value. So in this cell, we're going to start out with an empty list, and then 25,000 times we're going to add a new trial or a new result of a trial onto that list. And so we're just gonna keep adding trials or adding observations until we obtain 25,000 observations that are to be used in our simulation. So let's go ahead and grab those trials. And then in this cell, we're just going to plot up the histogram or the approximate distribution of our present value random variable that we get from these 25,000 observations. So whenever I ran this a couple of times before making this video, I was able to tell that the distribution starts to kind of, the tail of the distribution starts to kind of taper off around 1500. So I chose to cut it off there. As you'll see, the tail is obviously implied to go off to infinity and have you can have values anywhere from 0 to infinity on the positive real line, or on the non-negative real line. But for the purposes of this video, I felt that it was kind of all right to cut it off at 1500. And then we're gonna so the bins are just the bins on our histogram. So they span the range from 0 to 1500, and each bin width is 1. And we're just going to plot up our trials in those bins, and that's going to give us a visual of what our approximate probability density function looks like. So if you've had probability, you can maybe take a look at this and say, well, Austin, that kind of looks like an exponential random variable. And you'd be absolutely correct. This distribution fits really, really closely to an exponential random variable. And I think it's kind of interesting that, out of this kind of complicated distribution, we end up with something that looks like an exponential random variable. It's almost like it's almost like we kind of just scaled the exponential random variable that's the payment in order to get this distribution, which is a really interesting result. Something that I wouldn't have been able to immediately tell you just based on kind of looking at this formula and looking at the distributions of these random variables. So now we're just going to convert our list, our trials list, over into a pandas series, and we're going to use the describe method in order to grab some quick summary statistics. So all that the describe method outputs to us is it tells us our total number of observations, which is 25,000 as we defined in cell 3 up there. And then it tells us that our average is around 300. Our standard deviation is also around 300, which is, again, a pretty good indicator that that this follows approximately a, and I say approximately because those are not those each are not exactly 300, but it's a pretty good indicator that this follows an exponential random variable when the standard deviation is real close to the mean like that. And that just has to do with the second moment and the variance ends up being the mean squared, and so it ends up being that the standard deviation is equal to the mean. And so you end up with when you have the standard deviation really close to the mean, it's a pretty good indicator that follows something like an exponential distribution. So then it gives us our 5-number summary. So we got a min and a max, and we got a median, and we got the quartiles. And so that's kind of the numerical results on the part of our Monte Carlo simulation that helps us to sort of understand our data a little better. So, obviously, y'all can probably tell that this would just have a wide range of applications in a quantitative finance setting. And I hope that what you've seen in this video today helps you in developing your own models and helps you, to be able to kind of know a little bit more about how Monte Carlo sampling is done. I hope this example really helped. I think it was a pretty decent example to be able to showcase kind of the power of the Monte Carlo method. We're able to kind of take this really complex random variable, complicated random variable, break it down into its parts, estimate the distributions of its parts, and then put everything back together again. And that's really what you'll see time and time again in Monte Carlo simulation is that you simulate the components, you combine the components using a deterministic function, and then you aggregate your results, right? And so down here is us aggregating our results, just seeing kind of a visual representation and the numerical representation of our results and kind of how the distribution looks, approximately, but still a pretty good approximation. So, thanks for watching today. Go ahead and like the video, subscribe to us, give us a follow on Instagram, all that good stuff. Yeah, thanks for watching. I hope you learned something today, and y'all take care. Bye-bye.